Welcome once again in my class of network theory. In our last class, we have already learned about the concept of series RC circuit. In today's class, we will learn the concept of parallel RC circuit. We will see that what are the expressions of instantaneous current and voltage, what are the phase angle between them, and what are their RMS values, how to derive them, and we will also solve numerical based on the concept that we will be gaining today. So let's start the class. Now as we can see here that we have a parallel branch having a resistor and a capacitor, and across that parallel branch we are applying an AC voltage or AC sinusoidal voltage, and small v here it represents the instantaneous value of that applied voltage. And since this is a parallel branch, as we know that in case of parallel circuit, the voltage drop across every component or branch is same, and the current that flows through every branch may or may not be same. Now here the sinusoidal AC voltage that we are applying, if we assume that voltage as Vm sin omega t, since V is the common parameter between resistor and capacitor, so we are taking here the voltage as a reference. So here the phase angle will be 0 degree. So this is the instantaneous voltage applied across the parallel RC circuit. Now next we will obtain the current that flows through every branch. Now if we find instantaneous current through the resistor, then it will be simply by using Ohm's law we can find, and that is V by R. And if we put the expression of V or instantaneous value of V, then it is Vm sin omega t divided by R. Now next we will find the instantaneous current through the capacitor, and that, as we have already seen multiple times in our previous classes, that IC will be that is equal to C dV dt. Now in place of V, if we put this expression Vm sin omega t, and if we now differentiate once, then by the rule of differentiation it will be omega C Vm cos omega t, and Vm, as we know, is the peak or maximum value of the applied voltage. Now here, since the expression of the reference parameter, that is sinusoidal, and we are here analyzing the sinusoidal steady state response of RLC circuit, here in this case parallel RC circuit. So finally the expression of branch current will be also expressed in the form of sinusoidal. So here from cos to sin, if we want to transform, then cos omega t either can be written as sin 90 degree minus omega t or 90 degree plus omega t. But since we have to keep the omega t value as positive, that angle, so here we will be using 90 degree plus omega t, this format of the compound angle. Now next we will find the total instantaneous current in that parallel RC branch. That means the current that is supplied by this voltage. If we assume that as I, then I can be written as this branch. This current will be divided into two parts, and they will be flowing through these branches. So it is R IR, and this is IC. So here I will be summation of IR and IC. So in place of IR we will put this expression that we have already obtained, and in place of IC we will put this expression omega C Vm sin omega t plus 90 degree. Now next we will expand this compound angle by following the formula of trigonometry that we know. So it will be that the first term will remain same, and in place of second term we will be writing it sin A plus B. So it will be sin A cos B plus cos A sin B. So it will be sin omega t cos 90 degree, and then in the third term we will be having cos omega t sin 90 degree. Now we know that cos 90 degree has value 0, so the second term will vanish, and sin omega t has value 1. So the modified expression or the modified term on the right side of this equation in total instantaneous current, we will be having Vm sin omega t by R plus omega C Vm and only cos omega t, because sin 90 degree is 1. Now if we draw the phasor diagram of this parallel RC branch, then this can be done this way, since voltage we took as reference. So first we will draw the phasor of voltage, and this is V. Now next we will draw the phasor of the current that flows through resistor, and we know that the voltage applied across the resistor or voltage drop across the resistor and the current that flows through the resistor, between them the phase difference is always 0. So here when we will draw the phasor of IR, it will be simply they will coincide or they will be in the same line, because between them the phase difference is 0. So this is the phasor of IR. And next we will draw the phasor of IC. Now we have seen that the IC is leading the applied voltage by 90 degree. So in the phasor diagram, the phasor of IC will be leading the applied voltage by 90 degree. So the phasor of IC will be this. Now next we will complete the parallelogram and we will draw the resultant of that parallelogram, which is formed by IR and IC, and that will be the phasor of total current in that parallel RC circuit. So this will be the phasor of total current I. Now here we can see that I, this total current, is leading the applied voltage V, but here the phase difference between I and V is not 90 degree, rather it is less than 90 degree, and let's assume that as let's that mark as theta. So here the expression of current will have plus theta as I is leading V. So now on the left side, if we express this instantaneous value of the total current in terms of sinusoidal wave, then it can be written like Im sine omega t plus theta, where Im signifies the peak or maximum current of that maximum value of that total instantaneous current. Now here on the right side we are keeping the same terms. So next what we will do, we will expand this compound angle that we have on the left side. So here if we now expand this compound angle, then it will be Im sine omega t cos theta plus Im cos omega t sine theta, and on the right side we are keeping the same terms. Now what we will do, we know that we have already seen for several times in other circuits, that now next we will equate the coefficients of like terms. Now in this equation we have sine omega t and here we have 1 sine omega t. So first we will equate the coefficients of this sine omega t like term. So it will be this, and from the other terms, here we have 1 cos omega t term, and here on the right side we have another cos omega t term. So if we equate the coefficients, then we will be having first we are writing with the like term, like we are including the cos omega t, and in the next line we will be equating only, or we will be writing only the coefficients. So it is Im cos omega t sine theta, and here from the right side we are writing, or we are getting omega c Vm cos omega t. Now when we will be equating only the coefficients of like terms, then from this equation we will be having Im cos theta, and that will be equal to Vm by R, and from the second equation we will be having Im sin theta, and that will be equal to omega c Vm. And this is the concept that we have already seen in our previous few classes. So next what we will do, we will be finding out the value of the phase difference, means this theta phase angle. So for that, what we will do, we will take the square values and then we will add them, and then finally we will take the square root. So if we take the square values of both the sides of both the equations, then it will be Im square cos square theta plus Im square sin square theta, and then if when we will add these two terms, so Im is the common factor between these two terms on the left side that we have in both the equations. So Im square can be taken as common, and inside the bracket we will be having sin square theta plus cos square theta, which always gives us 1. So from the left side, or on the left side, we will be having Im square, and on the right side we will be having Vm square divided by R for this part. And for the second equation, or from the second equation, we will be having omega square c square, then Vm square. Now Vm square is the common term, so that can be taken as common, is the and then it will be 1 divided by r square plus omega square c square. So now next, if we want to get the value of maximum current, that can be written as 1 by r square plus omega square c square and then square root of that added values. So from here, if we now next we want to get the maximum current, so this is the value. So it is 1 by r square plus omega c square and then square root of that. Now we know that I, by Ohm's law, I is equal to the applied voltage multiplied by the admittance of that AC circuit, the net admittance of that AC circuit. Now here, since we have already seen that the current, the net current or the total current in case of be it series RC circuit or in this case parallel RC circuit, the net current always leads the applied voltage if we take the voltage as reference. So here, since Vm is the reference parameter, so the phase angle is 0. So definitely the phase angle of this admittance will be leading in nature, so that the phase angle or phase difference between this current and voltage, or the phase angle that we will be getting for current, that will be leading in nature, means the positive value. So the phase angle for admittance that we will be writing, that will be positive in nature. And now from this relationship, if we want to suppose find out the V, then we know V is equal to I multiplied by Z, impedance of that AC circuit. So it can be written as I divided by Y. So since Y has the leading phase angle, so this leading phase angle, when we will express, and when that phase angle will be in the denominator, and that will have the positive value. So when it will go to the numerator, then that definitely that will be negative in nature. Or on the other side, we can say that the phase angle of the impedance term, that will be lagging in nature. So in case of RC circuit, the phase angle of admittance is leading in nature, and phase angle of the impedance is lagging in nature. So this is the expression of admittance. We know admittance is G plus JB, where G is the conductance of that RC branch. So conductance will come from the resistance part. We know the conductance is the reciprocal of resistance. So G will be 1 by R plus JB, where B is the susceptance of that AC component. Here we have capacitance, so it will be capacitive susceptance. Now capacitive susceptance is reciprocal of the capacitive reactance, and capacitive reactance means 1 by omega J omega C. So it will be 1 by 1 divided by 1 divided by J omega C. So that means J omega C term finally we will be getting in the numerator, and that's why it has been written directly as 1 by R plus J omega C. And now this is the, as we know, this is the representation of this is given in rectangular format. So from here, if we want to get the polar format, or if you want to represent in polar format, then simply by using the formula that I have already discussed, that can be used. So it will be, by using that formula, it will be 1 by R square and then omega C square and then square root of that square value that we have already achieved here, obtained here. And angle wise, it will be tan inverse omega C R, and we know that format is basically R and then angle theta. So R value is this is the radius of that circle that it forms when it angularly moves. So R is that radius, and theta is the angle which it makes, that particular point makes with the positive real axis. So here, since we are finding out admittance, so the phase angle will be positive or leading in nature. So it is tan inverse omega C R. Otherwise, if suppose it was impedance, if we had obtained the impedance or calculated the impedance, then this we would have got the same value, tan inverse omega C R, along with the negative sign. Now next we will express the total current in that branch, and this time it will be the instantaneous total current. So I can be written as Im, the peak value, this is the format, then sine omega t, and then the phase difference between that total current and the applied voltage. And since we have already seen that phase angle is leading in nature, so it will be plus theta, and theta is that we can obtain from this two equations, like it will be that we have seen several times, that it will be Im sin theta and divided by Im cos theta. So it will be Im sin theta means omega c Vm and divided by 1 by r. So Im will cancel each other, then it will be tan theta, and then it will be omega c, and this r will go in the numerator. So theta means tan inverse then omega c r. So this is the way how we find the value of the phase angle of theta, and that value has been written in this place. So sine omega t plus theta, since this theta has been incorporated within the sine as compound angle, so we are not writing that theta, that angle here when we are representing the Im. So Im is Vm and multiplied by the admittance value. So admittance value will come from here. So Vm, and this is the admittance value. So this is the way how we can represent the instantaneous values of the branch currents, or also the total current, and also the phase angle between net current or total current and the applied voltage. Next, we will solve this numerical based on parallel RC circuit with the knowledge that we have already gained in this class. So here, as we can see, we have this R branch having value 10 ohm, and the capacitor having capacitance value as 100 microfarad, and we are here applying a current source which is supplying current 20 ampere, and frequency of that AC supply is 50 hertz. So from here, the values that we are getting, the information that we are getting is linear frequency is 50 hertz, the resistance value is 10 ohm, and also the capacitance value is 100 microfarad. That means it is 100 multiplied by 10 to the power 6 farad, and also this 20 ampere value is given. So this 20 ampere value of the current will be taken as the RMS value. So it will be IRMS will be 20 ampere. This is not the peak value, and also the expression of instantaneous current is not given this time. So from here we have to find the RMS value of the currents through R and C first. So here first we will calculate the individual admittance values of these parallel branches. So let's first find out the admittance of the resistive branch. So if we represent or denote that as YR, though admittance term doesn't fit with resistance, because here by admittance what we mean as this is simply the conductance of that path. That means it will be simply 1 by R, and since the phase angle is resistive path, so phase angle will be 0 degree. So it will be simply 1 divided by 10, and the phase angle will be 0 degree. That means it is 0.1 and then 0 degree. Now if this is polar format, so if we represent that into rectangular format, then it will be this R value 0.1, and then within bracket we can write cos theta means cos 0 plus j sin theta means j sin 0 degrees. So R cos theta plus j r sin theta means x plus j y. So from here cos 0 degree means 1, so it will be 0.1, and j sin 0 degree is 0, so it will be j, the complex part will vanish, it will have 0. So it can be written as 0.1 plus j into 0, and since this is admittance, so the unit of that will be mho. Now separately, if we calculate the admittance of the capacitive branch, and if we that represent as y of c, then it will be 1 divided by x of c. So as x of c itself is 1 by j omega c, so finally it will be j omega c. Or now if we represent that in polar format, then it will give us 90 degree angle. So here first we have to calculate the omega c value. Now omega means 2 pi f, and c value it's already given in the problem statement. Now 2 pi f is 50 and 2, so 100, and pi is 3.14. This is the approximated value. So finally it will give us 314, and the value of the capacitance is 100 multiplied by 10 to the power minus 6. So finally it will be 10 to the power minus 4. And the phase difference of admittance is, we know it is for purely capacitive circuit is 90 degree, and that is positive in nature, leading in nature. So finally it will be, the admittance value will be 0.0314, and if we expand this 90 degree in form of cos 90 plus j sin 90, means if we represent in rectangular format from polar, then it will be cos 90 degree is 0, and sin, this will be 90 degree, sin 90 degree is 1. So the real part will vanish and it will have only the imaginary part. So it will be j and then 0.0314, and this will be mho, the unit will be. Now next we will calculate the net admittance of that parallel branch. And admittance, they are when the two branches are connected in parallel, their admittance are simply added. That rule we know. So it will be yr plus yc. So it will be 0.1 plus, see, it doesn't have any imaginary part and it doesn't have any real part, so simply it will be 0.1 plus j 0.0314, and this unit is mho. Now this rectangular format, if we need to convert into its equivalent polar format, then by using the formula or by using calculator we can do that, and the final values are of r and theta in that polar format will be 0.105, and the angle, the theta, will be 17.43 degree, and that will be mho. So this 17.43 degree is the phase difference between total current and the applied voltage. Now next, if we, based on this value of the net admittance and the current value that we have, that is given in the circuit, which is 20 ampere, the IRMS. So next, if we want to get the value of the RMS value of the voltage drop across this parallel branch, then it can be calculated like V will be I multiplied by the impedance of that path, or we can say I multiplied by 1 divided by admittance of that path. So I, that value is 20 ampere, and the admittance value, net admittance, we have already obtained, which is 0.105, and angle we are not writing here because when voltage is taken as a reference, with respect to that the current leads by that net phase angle, which is here 17.43 degree. That means the phase angle of the voltage will be 0 degree here, so we'll only calculate the value, RMS value of that voltage drop. So it will be 20 divided by 0.105 will give us 190.48, and this will be volt. So this is RMS value. So if we want to express the instantaneous value of the voltage drop, then it will be now VRMS. So it will be Vm and then sine omega t. We know that the maximum value is RMS value multiplied by root 2, and then it will be sine omega t. So if we put the RMS value 190.48 and then if we multiply by this root 2, we will be getting the peak value of this voltage. Now requirement is to get the RMS values of the currents IR and IC. So the RMS value of IR can be calculated like the RMS value of the voltage, which is 190.48 multiplied by the admittance value, which is 0.1 and 0 degree. So finally it will be 19.48 or 048, and then angle, both the angles will be added, so it will be 0 degree. And definitely the phase difference between the current that flows through resistor and the voltage drop across that resistor will be 0 degree. Now next we will calculate the RMS value of the current that flows through capacitor. So it will be again the voltage value, which is common, which is same here, 190.48, and then here it is 0 degree, and that will be multiplied by admittance value of that capacitive path, which we have already obtained as J 0.0314. So it is given in the rectangular format, J 0.0314. Now this rectangular value in this rectangular format should be converted into polar format. So it will be 190.48, then 0 degree, and then it will be multiplied by 0.0314, and the phase angle will be 90 degree. So finally this value will be 5.98, and angle will be 90 degree, and the unit will be ampere. And these are the RMS values of those currents. So if we want to get the peak value of those currents, then that can be calculated as 19.0.48, and then phase angle is 0 degree. That will be multiplied by √2 factor. So it will be 26.94, and the phase angle is 0 degree, this much ampere. And then the peak value of that individually, if we want to get for the capacitive current, then it will be this value 5.98, then 90 degree, and then that will be multiplied by √2. So it will give us a value of 8.46, and then the phase difference will be again 90 degree, the angle value, and this much ampere. And if we draw the phasor diagram, then if this is V, say the phasor of the voltage drop across the resistor and capacitor, then IR, which has value 19.048, the RMS value, and this is 26.94. So if this is our IR, the phasor of IR, let's use another color, then this is IR, and for IC it will be 90 degree phase apart, and this will be leading in nature, so it will be IC. And now next if we want to get the phasor for net current, then it will be the resultant of this parallelogram. This concept we have already seen. So this will be the net current. This will be the phasor of the net current. So this is I, and this angle theta has value 17.43 degree that we have already calculated, 17.43 degree. This is the phase difference between the total current and the voltage difference, which is common. Now this is the maximum values and RMS values we have calculated. So this was the question in the first question, and then second question was the instantaneous value or expressions for those individual currents. So if we individually express IR and IC, then this can be written as the maximum value that flows through resistance. So it is 26.94, and this will be sine omega t, and this much ampere. And for IC it will be 8.46, and this will be sine omega t plus 90 degree. For purely capacitive circuit, the phase difference is plus 90 degree. So with this I end today's class. Thank you.